Thanks, Miko. Let me share the screen. Is it okay? Are you?
Yes, we can see it.
Yeah. Thanks, Miko, for the introduction. Hi, everyone. I'm now live from London. Hope you're enjoying the day so far. I'm part of the database engineering team at TransferWise, and during this talk, I'll share the implementation of MongoDB and how we managed to scale transfer service audit logs. But first, for those who don't know me, I work as a database engineer at TransferWise. I've been working for about 8 years with databases, mainly MariaDB, MySQL, and MongoDB. Outside work, I've been playing handball for nearly 30 years, and I also have interest in reportage film photography. So let me introduce you to TransferWise. It was established in 2011 by two Estonians. Nowadays, 2,000 people work across different offices globally. We have 7 million customers, and we process 4 billion pounds in transactions every month, saving customers 1 billion pounds a year. We serve 1,600 routes and offer more than 50 different currencies. Note that 25% of our international transfers are already instant. In order to accommodate the numbers I just shared with you, TransferWise has moved from an old monolithic architecture to run on hundreds of microservices. One particular service that takes a big part on the international transfer process is transfer service. Let's do a quick overview of this transfer service. As part of a distributed microservice architecture, transfer service listens to incoming topics published by other services like quote service for expired rates, paying service for messages like money received. It then processes these messages and publishes to outgoing topics for state changes or attribute updates. Internally, TransferWise Model acts like a complex finite state machine. The transactions you are seeing, the transitions you are seeing are just shortened version and only a very small part of this entire complex state machine. From a new state, it can go to paying initiated state, to received money state, to receive but waiting for recipient detail state. It could be sitting behind fraud checks or reaching the final states for transferred or canceled states. Each of the following, like state change or update of any transfer attributes, like estimated transfer time or currency conversion, generates a log which we call internally as audit logs. In average, each transfer generates 50 of these audit logs. These logs are required by different regulators and used by our ops agents to investigate any abnormalities. Let's go through some transition examples and log generation. Every transfer starts with a state new. In this case, the new state is paying initiated and the log of update type is generated. In this example, the new state is waiting for recipient details and the log of type updated is generated. From waiting for recipient details, this transfer makes another transition to received state. Again, another log of type update is generated with the new and old state. Further down in the state machine, a transfer can have some of its attributes updated. In this example, the transfer was subject to a discount, and the attribute discount and its value was added to the transfer. Part of TransferWise mission is to make sure people receive money instantly. To achieve this, our engineers are constantly working towards overcoming any technical bottlenecks. Let's look at transfer service case study. The former setup of transfer service was based on a MariaDB RDS cluster deployed on multi-availability zones. It was hosting over 1.5 terabytes of data plus indexes. Audit logs were responsible for nearly 45% of total workload, and it was handling mostly write operations. So when transfer service engineers started facing some slowdowns, they contacted the database engineering team to help them. We identified some issues and outlined some scalability problems on their service. Sudden increase of write latency, existing indexes, although not fragmented or bloated, they were not append-only. We looked at partitioning, but we couldn't find any suitable strategy to accommodate the different query shapes. And last but not least, we couldn't archive or delete data due to regulatory requirements. The graphs on this slide are a vivid Cortex snapshot representation of the average write latency and the number of audit log insert operation calls for a period of 8 weeks on the former setup. It is clearly noticeable that there was a sudden increase in average write latency from 6 to 13 milliseconds. On the other hand, the average number of 200 calls per second hasn't increased. So we question ourselves, if we currently have this performance degradation, what should we expect for the next months or years? So by looking at our growth projections, we knew we had to act quickly to prepare ourselves for the growing need and to perform at a higher volume. But one thing I want to make very clear is that even though we are keen users of MariaDB, nearly 40% of our database fleet runs on MariaDB, and we love it, honestly. We discovered that it is not fit for this specific purpose because of the scale-out limitations. We then decided to use MongoDB, but why MongoDB? Transfer service audit logs are not relational, and that's a fact. It gives almost unlimited transparent scale-out. Due to our growth projections, we already identified that we will have to move more and more non-relational workloads into MongoDB. MongoDB also increased our availability by allowing rolling maintenances with minimal impact. One of the limitations in MariaDB RDS is that major upgrades are in place, and they usually imply a long downtime to perform this operation, which is something we cannot longer afford. Also, failovers in MariaDB RDS take between 1 to 2 minutes compared to MongoDB, where we can experience failovers of few seconds. TransferWise is a global company and serves customers globally. Segmenting data by location feature allows us to be closer to the customer, reduces operations latency, and increases our customer experience. We also identified other existing workloads that run on relational databases that fit perfectly in MongoDB. And we already had the required expertise within TransferWise database in. Let's look how we deploy MongoDB at TransferWise. This is the example of transfer service audit logs current deployment. We deployed every component of the MongoDB sharded cluster across 3 different availability zones to minimize the effects of unavailability. We also use Percona server for MongoDB 4.2, and we also automated this deployment using a combination of Terraform and Ansible. As you know, proper data modeling is the single most important task to achieve excellent performance and scalability in MongoDB. From this background, let's see how we applied it to transfer service audit logs. We actually had to go through 3 different data model iterations. Let's go through them. This first iteration in MongoDB is an exact one-to-one match of the data model in MariaDB. 1 document per each audit log, where its ID is the document ID. For the indexes, we would end up with 3 indexes. 1 unique index on the ID field during the creation of the collection. The second one would be ID hashed for sharding purposes. And the third one, a composite of transfer ID and date to give back all audit logs based on transfer ID ordered on date. In MongoDB, this model gives us the best scalable write throughput because we have insert-only operations. However, it produces scatter-gather fine queries when querying for all audit logs for a specific transfer. The second iteration is a bit different from the first one, so let's see. We have 1 document per transfer and an array of embedded documents, each one being 1 audit log, defined by change fields. Whenever an audit log is generated, there is an upsert operation to append a new document into the array of audit logs. In this model, transfer ID is the document ID, and is generated by the service. For the indexes, we end up with only 2 indexes. Again, 1 unique index on the ID field during the creation of the collection. The second one is ID hashed for sharding purposes, which also covers our find queries on transfer ID. There are some advantages of this model compared to the previous one. We have less indexes in this model, which can translate to increased throughput and cost savings on storage. Although average document size in this model is slightly bigger than the previous model, we calculated that we could save on storage for an expected average of 50 audit logs per transfer. With less indexes and smaller data footprints, this data model gives us 44% less disk usage per transfer compared to the first iteration. The third and final iteration uses the exact same schema model as the previous one. There is one particularity, which is the application of one of the several best practices indicated by MongoDB, the use of shortened field names. This gave us even smaller footprint than the previous iteration per average transfer. One of the drawbacks of using shortened field names is that fields can lose their meaning. We then decided to create a single document for field mapping in another collection. This will help all engineers and our analysts when using downstream replicated data from this MongoDB cluster into our ETL pipelines. There are some advantages that are shared across all these three data models. Sharding on ID hash makes it possible to use the pre-splitting technique. This allows us to create the chunks ahead of time and well distribute them across the shards before beginning to insert data. When new and historical audit log data ingestion started, data went straight in the shard who owns the chunk referred to the inserted shard key. This translated into less chunk splits, less chunk moves, less latency, and less overhead. We also calculated the number of initial chunks to pre-split and distribute the chunks based on historical data living in MariaDB. So how did we actually calculate this number? We used the famous Grecian formula. The Grecian formula is named after Antonios Yiannopoulos, a dear friend of mine you most probably know, who happens to be Greek and gave a great talk earlier in the day. So how does this formula work? First, you need to get a sense of the orders of magnitude involved. In our case, we performed some data ingestion tests with real historical data existing in MariaDB and managed to get some statistics, which helped us to calculate the different variables needed for this formula. With regards to the number of shards and cost-effective resource configuration, we realized that it would be enough to hold our indexes and working set in RAM. Let me take you for a quick overview on how we managed to migrate historical data into MongoDB. For new transfers, their state changes and attributes updates, transfer service publishes these audit logs to Kafka. Using MongoDB Kafka connector, audit logs are then persisted to MongoDB. With regards to historical data migration, the database engineering team provided a MariaDB RDS read replica to avoid any disturbing production traffic and offloaded this migration process to the transfer service team. Simply, this process would gather a batch of transfers and their audit log rows from MariaDB, build the transfer JSON documents, and persist them in MongoDB. Let's now look at storage and resource costs. With this migration, we could achieve around 85% compression on disk. This is mostly due to wire tire compression, less indexes in this MongoDB model, and index prefix compression feature. With regards to the cost projection, by the end of next year, we expect a decrease of 50% compared to the costs we would have with MariaDB RDS. Although we use a big number of computing resources in MongoDB, for our case, MariaDB needed more powerful computing resources, more disk space, and more provisioned disk IOPS compared to MongoDB. This cost effectiveness is always taken into consideration because another part of TransferWise mission is to move money eventually free. Now, let's move on to performance evaluation based on service-side metrics. Insert operations in MariaDB were taking an average of 13 milliseconds with an average throughput of 6,000 calls per minute. Traffic spikes cause inserts to take longer. It's quite a noticeable change in query time. For the select queries, they were taking an average of 5 milliseconds. Upserts in MongoDB are taking an average of 5 milliseconds for the same throughput average of 6,000 calls per minute, and are almost 3 times faster compared to MariaDB. Part of this upsert time is because of network round trip between availability zones. We use write concern majority and JSON document parsing. These numbers we got them when we profiled the code calls with opsin. Traffic spikes of 5 times is barely noticed for the upsert query time. And for the find queries, these were taking an average of 1.7 milliseconds. We believe this was a great story, and we wouldn't achieve this without help of transfer service engineering team. As a result, service teams at TransferWise are already moving more and more non-relational workloads into MongoDB. So that's it from me. I hope you enjoyed this talk and was able to keep everyone awake in this 24-hour marathon of great talks. And now I'm happy to answer your questions. Thank you.
Thank you, Pedro. Well, there are still a few hours ahead, right? So I hope we'll all be awake. Yeah, we still have a couple of minutes for questions. So first question from Slack channel from Matt is like, there are some great savings over MariaDB RDS. Did you consider other database engines as well, or was it down to MariaDB or MongoDB only?
In terms of these audit logs?
Yeah, so basically, I think that the question is like, if you look at other alternatives than
Okay.
than MongoDB and MariaDB that you had before.
Yeah. So we consider we are hosted in AWS. So one obvious choice we considered was DynamoDB to answer this like NoSQL workload. But it's a very delicate question because I'm not here to compare like performance like between DynamoDB and MongoDB, but we chose MongoDB mostly because of its features. First, it has really easy integration with our observability stack. It also integrates with our ETL pipelines using the MongoDB change streams. We also analyzed existing different workloads that will have to be migrated into MongoDB. And a lot of them would benefit a lot from the MongoDB aggregation framework. And also the segregation data by location. It's something we are looking at. We have customers that live in countries that due to regulatory requirements, data has to live only in that region. And we also had expertise in-house with MongoDB, and plus we thought that not being locked in with AWS was a good option as well.
Mm-hmm. Mm-hmm. Okay, thank you. So another question for audit logs, usually writes are the operations which should be prioritized. So why did you go with an upsert instead of insert?
It's a good question. We had to wait between the current performance and the infrastructure costs, because we are dealing with a customer's money. Like we have to make sure that we spend on how and what we spend our money, right? So the latency and the performance that MongoDB with the upsert operations were giving to transfer service was more than enough. So there was no like reason to increase performance and increase as well the operational costs.
Okay. And another question, how has been the adoption of MongoDB at TransferWise by other services other than audit logs?
So TransferWise persisted, like historical persisting layer has been relational. This transfer service deployment in production was actually the first one we had. And so in a way, it takes time to change mindsets internally, but the adoption has been slow and steady. It's something we need to be very conservative as well. But we already have in the pipeline a lot of use cases like this one to migrate workload that actually fits much better in MongoDB.
Mm-hmm. Mm-hmm. Okay. Yeah, I think we have no more questions. So thank you very, very much, Pedro, for this presentation. It was very informative.